So now we are going to be looking at Laplace transform in today's topic. Are we together? You see this Laplace transform, it is a tool that we can also use to evaluate some integral. But what we want to look at here is that we'll look at how to evaluate Laplace transform. The Laplace transform of different functions. We will learn inverse Laplace transform. And the application we are learning here is the Laplace transform, is how to use Laplace transform to solve ordinary differential equation. Yeah, so let's go. So what is the definition of Laplace transform? Now pay attention. Let's assume that we have a function of f of t. Then what is the Laplace transform of a function of f of t? What is the Laplace transform of a function of f of t? Now, this is the definition. The Laplace transform of a function f of t is equals to the integral from 0 to infinity. Integral from 0 to infinity e to the power of negative st times f of t dt. Integral of 0 to infinity e raised to the power of minus st f of t dt. Now, keep in mind that you see the Laplace transform of this function f of t. Our answer will always be a function of s. Please keep this in mind. This is very important. Whatever Laplace transform we evaluate, it will always be in terms of s. Are we together?
Yes.
Yeah, it is a real variable. Good. It's an arbitrary real variable. Good. All right. So this is defined for t between 0 to infinity. Yeah. Exactly. So let's go. Now, the thing is that we have some condition for Laplace transform to exist, but we'll not be looking at that for now. Let's quickly go into the main Laplace transform. That can be given as assignment. Now, let's go. You see, after knowing this Laplace transform, we are not proving here, actually. So pay attention to something. Now, let's discuss some of the properties of Laplace transform. Let's discuss some of the properties of Laplace transform. Some of the properties of Laplace transform. Yeah. So let's go. Now, pay attention to something. Let me say, throughout this lesson, wherever you see Laplace transform of function of f of t, of a function of t, take note that what it is what f of s. Also, if I say Laplace transform of a function g of t, I'll write it as g of s. Don't forget, whenever you evaluate Laplace transform, your answer will always be in terms of s, where s is an arbitrary real variable. Good. Now, pay attention. Talking about the linearity of Laplace transform. It's talking about what the linearity of what Laplace transform. And what is it? Pay attention. If I have Laplace transform of a times f of t plus b times g of t, a and b are some constant. Now look at it. What does it mean? Pay attention that it is possible for us to separate Laplace transform for these two functions. And it is possible for a constant to always move out of the Laplace transform. Therefore, this one becomes a times Laplace transform of f of t, then plus b times what? Laplace transform of what? G of t. Exactly. You can see it's possible for it to move out. And don't forget, Laplace transform of f of t is given as f of s. So this a f of s plus b g of s. That's it. A f of s plus b g of s. So that is what? The linearity of Laplace transform. So it's possible. It's possible for plus and minus. Plus and minus. This is very possible. Another property is this. Pay attention. This property is what we call first shifting property or first shifting theorem. First shifting theorem. Now, this first one is what we call linearity. This is what we call linearity of Laplace transform. Now, this one is what first shifting theorem. Now, what's first shifting theorem telling us? Now, pay attention. Don't forget that if I say Laplace transform of f of t will give me a function of s. Don't forget, the Laplace transform of the function of t will give me what? F of s. Now, the question is this. How will you now find the Laplace transform when exponential is now multiplied with it? Let me say exponential of 8t is multiplied with this f of t. What will it be? Whenever exponential is being multiplied with your function and you want to take the Laplace transform, then we use what we call the first shifting property. Are we together? Are we together?
Yes, 100%.
Hello, are we together? We use the first shifting property. Where do we use first shifting property? Whenever we have what? Exponential multiplying our function of t, then we want to find the Laplace transform. What will it be? Now, pay attention. Don't forget, Laplace transform of f of t is f of s. Now, whenever exponential is multiplied with t, you just come to where you have your s and subtract this coefficient of t on the exponential, which is a. Subtract it away. Then, this is the first shifting property. Let me give you another example on this. If I have Laplace transform of exponential minus 8t of f of t, how do we evaluate this? Now, check. Remove, subtract the coefficient of what? Of t that you have on this exponential. Subtract it from the s. So what do you have? What do you have? Can you tell me? Do you know?
I don't
remember. A, pay attention. When it was a, we come here and minus the a, and this is what we have. Now, yes. If it is minus a, we also come here and minus the minus a. Do you get? So what will be my answer?
That will be plus a.
Exactly, plus a. That's it. Don't worry. You understand what this thing means later. Just take note of this. This specialty property is very important. Like, very, very important. Nice. Next one, number 3, is that how do we remember this thing with Laplace transform f of s? Now, when exponential is multiplied with it, this is what we have. But what if I have a function of t multiplying the Laplace transform and multiplying the function? Now, check. We now have a function. Now, if the exponential is multiplied with it, this special property. Now, t to some power is multiplied with that function. What do we have? You now do something like this. Pay attention. You say minus 1 to the power of n to the n that you're having. If you're having 2 to the power of 2, you're having 1 to the power of 1. Then you now find the nth derivative, the n, the Sn of the Laplace transform f of s. Now, pay attention. Don't worry. It's simple. It's simple. Don't worry. It's very simple. Don't worry. That's why I doubt if we rush. In fact, this part is, from this part onward, they are stronger engineering maths. So I prefer probably we are doing it maybe today. We'll do it tomorrow. But if you finish everything in a class, it can confuse you. Okay?
Okay. Let's do it once more.
Yeah, no Allah. So just check this one like this now. Whenever, don't worry. We are going to solve questions. Don't worry. I'll solve question on this property. Do you understand? Don't worry. Okay?
All right.
Yeah, no Allah. Just let's go. So just observe this. Don't worry. Whenever I'm solving question, you will see the application now. So number 4. Another property we are going to be looking at is how do we find the Laplace transform when we divide by t? When we divide by t, how do we find the Laplace transform when we divide by t? Okay, so you just say that, okay, you have infinity, 0, integral 0 to infinity. Sorry, not 0, sorry, that's s. If you are dividing by t, integral from s to infinity, then what do we have? F of, wait, let me see. I think this is f of s ds. Yeah, f of s ds. Yeah, f of s ds. Good. F of s ds. Okay. Have you seen it like that? Is that okay?
Yes.
When you divide by t, this is how you evaluate. Now, pay attention. Let me now give you another property for Laplace transform. Laplace transform of integrals. Now, pay attention to this. Very important. How do you find Laplace transform of whenever you have integration? Yeah, now look at it. Let me give you this powerful property. So check. If you want to find Laplace transform of, let me see the integral from a particular constant a to t of f of t dt. Now, how do you find Laplace transform of integral? Now, pay attention. It is equal to 1 over s integral from a to 0 f of t dt plus 1 over s Laplace transform of f of t. Now, look at what is here. 1 over s integral a to 0. Now, look at something here now. I want to work on this Laplace transform of integral. Let's assume that a is 0. Assuming a is 0, it means that you want to find the Laplace transform of integral from 0 to t f of t dt. Oh yeah, how do we do it? Then substitute 0. If I put 0 on this one, what happens to the integral? It vanishes. Have you now?
Yes.
Please hold on. Give me some seconds. I'm coming.
All right.
Okay. I'm coming. Ahead. Now, see what we have now. So, look at this limit now. So, these limits are now the same thing, 0, 0. So, this one will cancel out. Are we together?
Yes.
Good. Then, what they have? 1 all over s, Laplace transform of f of t. And don't forget, Laplace transform of f of t, I can write it as 1 all over s, f of s. Do you know that? It means that if you're having this integral like this is your answer. Laplace transform of integral of 0 to t f of t dt is 1 over s f of s. That's all. So focus on this part very well. This part is general. If they want to trick you, what if a is not 0? Just make sure that you add this term to it. Okay?
Yeah.
Exactly. So that's Laplace transform of integral. Next one is Laplace transform of derivative. Laplace transform of derivative. Please hold on. Please hold on. I'm coming. Now, let's continue, please. Now, the next one is Laplace transform. We have done Laplace transform of integral. Can you hear me?
Yes, I can hear you.
Now, next, now do Laplace transform of derivative. That's number what? That's what property
6.
now?
Yes, number 6.
6, okay. I want to look at Laplace transform of derivatives. Laplace transform of derivative. No, I'm coming. Let's look at Laplace transform of derivative. Since we have looked at integral, now you see this aspect. That's what you will use to be solving differential equation. Are we together?
Okay.
This is the aspect that will majorly help you to solve differential equation. Now, pay attention. Let me give you the general formula. Now, the Laplace transform of derivative. Now, here my derivative is c. Remember, I can write dy dx as just me saying f prime. You know that?
Yes.
Exactly. Just like you can just write prime. Good. So here now, let me write fn. Laplace transform of, now this derivative, like this means nth derivative. So what does it mean? Let me show you. Laplace transform of n derivative is, firstly, s raised to power n. The f of s. Remember what f of s means? F of s means what? If you can remember, f of s means Laplace transform of f of t. Have you now?
f of t dt.
Yes. So f of s raised to power n f of s minus s minus 1 f of 0. Don't worry, I'm coming. This small letter f. Don't forget f small letter f really. So then minus s power n minus 2 f prime of 0. Don't worry, I will show you something. Minus Let me just, I'm coming. Dot dot dots up to f raised to power n minus 1 of 0. Have you tried other device?
Yes,
Yeah,
my
then
system is almost dead.
which one of them? Which one of them? Which one of them? You have
Sir?
muted one, right?
Yes, I'm going
Yes.
to
If you don't do that,
exit from.
go to yeah. Now let me explain this thing for you. Now pay attention. This one, if you cram this one, you can make error. Now let me just teach you something. Let me say, for example, now you want to find the Laplace transform of let me say fourth derivative. Let me say of fourth derivative. How do you do it? How do you find Laplace transform of? Okay, let me write this in a notation that is easy. Now let me say you want to find d4y over d4 f of t all over d t to the power of 4. Now, d is to the fourth derivative. So how do we do it?
To equal to.
Firstly, you will bring this power first, s raised to power 4, and you just find the Laplace transform. That's f of s. That's the first thing. Are we together? You first
Yes.
bring s, then you put this power that you have, then minus the power of s will start decreasing. Now, pay attention that after this thing, the next one is that you have s cubed, then you have f of 0. You see this first thing, that's what you should tell your memory. You first have s to the power that you have, f of s, the Laplace transform, then minus, reduce 1 from here, s cubed, then small letter f of 0. Then after that, exhaust the remaining s on derivative. Don't worry, I'll write this for you in what? That is, then, exhaust the remaining s on derivative. What do I mean? Derivative. Now, what do I mean? Now, let's go. This s is power 4, f of s, minus s cubed, f of 0, then minus s squared, f prime of 0, minus s, f prime prime of 0. Are you there? What else again? I still have s remaining. Are you there?
Yes.
Then what do I have? Minus s has
Minus.
finished. So s raised to power 0, f prime prime or
Or
now,
0.
if you want to know you are correct, if you want to know you are on the track, there are some things that you should check. Number one, endeavor that the power of s are reducing by 1. Secondly, the last derivative that is here is always 1 less than what you have here. Check nth derivative. My last derivative is n minus 1 derivative. Here, I'm having fourth derivative. And the last thing I'm having here is what? Third derivative. Do you get that?
Yes.
Okay, let me say I have Laplace transform of, let me say I'm looking at the third derivative now. I'm looking at the third derivative. Now, what do I do? Firstly, I have s raised to power 3, f of s. Are you there?
Yes.
Then minus s squared. The next thing that must follow it must be f of 0, not derivative. Are you there?
Yes, I'm with you, sir.
Then the last thing is that you now adjust the remaining s. Mute one of your devices.
No. All of them are muted.
It's like you're having call.
Oh. Let's continue.
Okay. Now, so what do I have left?
It's still going to remain just
S as
F prime of 0.
if you observe S second derivative. Please mute your device. Mute one of them. It's echoing.
Okay, somebody is calling me.
I was listening that.
All right, let's continue. Yeah.
So next one, convolution theorem. Convolution theorem. Now let's look at convolution theorem. Are we together? Are we together? Now,
Yes, we are together.
so look at the definition of. Hello, you having two devices? Abi?
No. One.
My voice is echoing.
Ah. I don't know. It's not from my end. I don't have any call again.
Okay, no problem. Okay. We define the convolution of two functions. For example, now check the convolution of two functions, f of t and g of t. This is the definition. It's defined by this. Now check. If you see this asterisk you see here, it means convolution. Are we together? Yes. This asterisk you have here, it means what? It means convolution. Now, what is the convolution of two functions? For example, you are asked that you have two functions, f of t and g of t. What is the convolution of those two functions? So you say f of t asterisk g of t. This asterisk that I are seeing here is telling you the convolution of f of t and g of t. You see this convolution that you're having here is the integral from 0 to t f of u, then g of t minus u du. This is the convolution of two functions. Exactly. If you ask to find convolution of these two functions, this is what you have. Exactly. This is what you have. So that u that you are seeing is another new variable. And pay attention that it's possible for you to invert this. I can also say integral from 0 to t. I can say g of u, f of t minus u du. I can invert it, there's no problem. So this is the convolution of two. Anyone can come first, so it's the same. This is the convolution of what? Two functions. Now, what's now the convolution theorem? So what's now the convolution theorem? What's now the convolution theorem? Now, let's go. Are we together?
Yes, 100%.
Yeah. Don't forget that. Now, mute yourself. If I ask you anything, you can mute. Yeah. So now, if you have the Laplace transform of the convolution of two functions, now check. If you have the Laplace transform of the convolution of two functions, what will it give you? You see, the Laplace transform of the convolution of two functions is equal to the product of the Laplace transform of the two functions. What am I saying? Check. The Laplace transform of the convolution of f of t and g of t is equals to, now check, the Laplace transform of f of t times the Laplace transform of g of t. It means that Laplace of the convolution of two functions is equal to the product of the Laplace, which means, don't forget, this is equal to f of s, then times g of s. So this is the convolution theorem. So don't forget that to have the product of Laplace transform, it means that you are doing convolution of the two functions. Is that clear?
Yes, sir.
Exactly. So now, since we've learned this, we've learned all these properties now. Okay, now pay attention. Let us now learn. Hold on. Now, from beginning of this class, we've learned the definition of Laplace transform, the properties. These properties are very important. All this I'm teaching you now, they are all properties. Now, the next thing is that we now want to learn the Laplace of some elementary functions. That is the Laplace of some elementary functions. The Laplace of some elementary functions. Now, pay attention. You see, let me tell you one short story about this thing. You see, this thing that you want to learn now, everything were proved from this definition. Everything. But yeah, I promise not to prove anything. But if we prove and use integration by parts, you'll be getting all this. Now, pay attention to something. If I have, look at the first that I want to learn. How do you find the Laplace transform of some powers of t? If t is carrying some powers, how do you find the Laplace transform? Now, here now, this is my f of t. So here now, this is my, what you're having here now is my f of t. So my f of t is now t carrying some powers. So how do we do it? Our formula is equals to n factorial over s raised to power n plus 1. That is it. N factorial over s raised to power what? N plus 1. Now, example. If I tell you that, okay, find the Laplace transform of 1, how do you do it? You can use this to find Laplace transform of 1. Don't forget that Laplace transform of 1, I can write it as Laplace transform of t to the power of 0. And these some powers of t. I want my formula 0 factorial over s raised to power 0 plus 1. 0 factorial is 1, then 1 over s. You are done. So it means that Laplace transform of 1 is 1 over s. Are we together? Are we together? Are we together? So let me ask you something. If I ask you that, what's the Laplace transform of 2? You see, Laplace transform of 2, don't just trouble yourself. This is the same thing as Laplace transform of 2 times 1. And I can bring this 2 out. It will give me 2 Laplace transform of 1. And what Laplace transform of 1? 1 over s. So I have 2 times 1 over s, and that's 2 over s. So Laplace transform of 1 is 1 over s. Laplace transform of 2, 2 over s. Laplace transform of 10, 10 over s. Laplace transform of 100, 100 over s. Do you see that?
Yes, 100%.
Exactly. Exactly. So similarly, if I have Laplace transform of, let me say I have Laplace transform of, let me say c cubed. How do I do it? I'll just follow this formula. 3 factorial over s raised to power 3 plus 1. And that's 6 over s to the power of 4. That's all. That's the first Laplace transform that you should know. So another one is this. How do we find the Laplace transform of e to the power of 8t? E to the power of 8t. Now, this number is my f of t. Now, we can get this Laplace transform without cramming anything. Now, don't forget, please pay attention to this part. Don't forget when I discuss this first shifting property of Laplace transform. This, that if you have exponential multiplying f of t, just go to the Laplace transform of that f of t and subtract a from it. Now, that's what I want to do here. Now, pay attention, maximum attention. Don't forget that here I can write it as Laplace transform of exponential at times 1. Now, check. Exponential is multiplying by 1. Don't forget, firstly, what is the Laplace transform of 1? What Laplace transform of 1? 1 over s. Now, since exponential is multiplying it, and the power of that exponential is 8c. Now, go and subtract this a from the s you're having there. So my answer is 1 over s minus a. That's it. 1 over s minus a. So you don't have to cram anything up there. So 1 over s minus a. So Laplace transform of e raised to power 8t is 1 over s minus a. So don't just disturb yourself. Now look at this one now. Next is number 3. You want to find the Laplace transform of cos, let me say cos omega t. Now this cos now. How do we do it? The formula is s over s squared plus omega squared. S over s squared plus omega squared. Now, you will see. Let me write the one of sine, and I will not tell you how to remember them. So Laplace transform of sine omega t is equals to omega over s squared plus omega squared. Now, do what I always do. If you look at cos, the last alphabet you have there is s. So remember that is s that will be above. So cos, it will be s over s squared plus omega squared. Yeah. But this one is going to give it s. You know it's omega that will be at the top. That is it. Nice. Next one is, how do we find the Laplace transform of hyperbolic function? That's cos t cos omega t. What will be our answer? It will be what? Do you know?
I don't know.
It's very
It's
simple.
very
Just
simple.
follow the
Just
same
follow
rule.
the same.
It will be
It will be
s
S
over
over
s squared
S
minus
squared
omega.
minus omega.
What's different?
What's different?
The sign, the plus and the minus.
Exactly.
Now tell me what would this one be? I'll tell you
Yes,
this
this
one.
will be omega over s squared minus omega squared.
Exactly.
Exactly.
So this is what you need to know. You don't have to even cram anything. Okay, now let us play around this thing. This is actually where we will stop. This is actually where we will stop. So let us now solve question on all these things that we have just learned so far, so that it will not confuse you at all. Because if they go back from this place, you can get lost. Now, let me check out some questions. Please give me some seconds. Okay, now let's solve this Laplace transform. This is like exercise to make you get used to the functions very well. All together. Now,
Yes.
the first question is this. Let's find the Laplace transform of
Laplace transform.
3t plus 12. So don't forget, I can separate the Laplace transform to be 3 Laplace of t, 3 Laplace of t plus 12 Laplace of 1. Okay, don't forget that. What is the Laplace of the function of t? Don't forget that if I have Laplace of t to the n is n factorial over s is power n plus 1. So what I'm having here will be, this will be 1 factorial over s is power 1 plus 1. This one, Laplace transform of 1 is 1 over s. We've learned that before. So this will give me 3 over s squared plus 12 over s. Then if you like, you can turn this to a single fraction. This s squared 3 plus 12s. Yeah, that's our final answer. So question 2. We have to find the Laplace transform of a minus bt squared. A minus bt squared. How do we get this? Firstly, let us go and expand this thing. If I have a minus bt squared, what would that give me? I have a squared minus 2abt, then plus b squared t squared. So therefore, the Laplace transform of a minus bt all squared is equals to, if I will Laplace all this, remember, all these are constant. A squared is a constant, 2ab is a constant, b squared is a constant. What we are concerned about is our t. So here I will write a squared Laplace of 1 minus 2ab Laplace of t plus b squared Laplace of t. Laplace of t squared. Yeah, Laplace of t squared. So what will this one give me? A squared times Laplace of 1 is 1 over s minus 2ab. What Laplace of t? Don't forget, Laplace of t has been done here. If you can remember, what Laplace of t? Check 1 over s squared. 1 over s squared. So I have 1 over s squared. Or you can decide to show the working if you wish. That's 1 factorial over s is power 1 plus 1 plus b squared. Laplace of t squared. Don't forget, there were 2 factorial over s is power 2 plus 1. So what is my answer? A squared over s minus 2ab over s squared, then plus 2b squared over s cubed. So turn them to a single fraction. So that will give me a squared s squared minus 2abs plus 2b squared. So that's the final answer. Hope you are getting it.
Yes, sir. Yes,
So
sir.
number 3, Laplace of cos pi t. Laplace of cos pi t. This is the same thing as, don't forget, recall that the Laplace of cos omega t is equal to s over s squared plus omega squared. So my omega here is now my pi. Yeah, my omega here is now my pi. So just substitute, you are done. So therefore, Laplace of cos pi t is equal to pi over s squared plus pi squared. Oh, sorry. That pi is s. Sorry, s. This is s. Because that's cos, so you start with s over s squared plus pi squared. Number 4, you have Laplace of cos square pi t. No, cos square omega t now. Now, looking at this thing, you observe that all our identity, we never had Laplace transform of, like we don't have any identity for powers of sine or cos. But this is how you are going to tackle it. Firstly, bring out this guy and deal with it first. Cos square omega t. This is what you want to deal with. Now, recall something. Recall that if I have cos square x is the same thing as 1 plus cos 2x all over 2. This is why trig identity are very important. So here I can write it as 1 over 2 plus cos 2x over 2. So I want to use I will now use the Laplace transform on them. So it means that Laplace transform of cos square omega t is equals to what? Half Laplace transform of 1. Don't forget, this is a constant. And this half under here again, I can bring it out. Half Laplace transform of cos 2. Cos 2 what? Cos 2. What do I write? Now check. My x says my cos 2 omega t. Is that correct?
Yes, this is correct. Yes.
Yeah, it's correct. Check, because see my x here now, cos square. So this is the whole of my x, this is the whole of my x. So this is the whole of my, so it's correct. Now, what my answer here? 1 over 2. Laplace transform of 1 is 1 over s. 1 over 2. Don't forget, cos s over s squared plus. Check, what do I write here? 2w squared. It's better you understand this thing very well, because when we get to inverse Laplace transform, we'll now be doing like a reverse of all these things. So that's 1 over 2s plus s over 2 s squared plus 4 omega squared. Yeah. So if you like, you can combine all this to a single fraction. Our LCM is 2s squared plus 4 omega squared. So what would this one give me? This will give me s squared plus 4 omega squared plus x squared. So this and this will cancel, so you have s squared. So my answer is 2s squared plus 4 omega squared all over 2s, s squared plus 4 omega squared. Now, interesting thing is that we are going to keep all this answer. When we are now learning inverse Laplace transform, we will now come and take inverse of this guy. We'll take inverse of this guy and we must return back to cos square omega t. Yes, so we are going to keep all these answers. Yeah, we are going to keep all these answers. Another question. This question what? 4. Question 5. Hello, hope you are following closely.
Yes, sir.
So we want to find the exponential, the Laplace transform of exponential 2t shine t. Exponential 2t shine t. How do I get it? Now, don't see, if you first see exponential multiplying anything, don't panic. This is the first thing you should do. You first go and find the Laplace transform of the function that is multiplying. What Laplace transform of shine t is what? Is what?
S squared over S squared.
What is it? What is it?
I said Laplace transform of shine t is omega.
Now, omega is not here.
Okay.
1.
Eh?
What is it? Wait, I'm coming. Exactly. Now, it's 1. So what do you say?
So this will be 1 over S squared minus 1.
1, exactly. No, you have gotten to now find the Laplace transform. This. Just come here. From this S, this 2. So now S minus. This is what we call first special theorem, which is f of S minus. This is now what? Yeah.
To confirm.
Do you understand now?
Exponential. We wrote exponential 2t.
What is it?
Exponential 2t. That was
this 2 bongo. You just come and subtract.
Yes, but like you wrote minus 1.
Where is it? It's here. Inside the C.
Oh, okay. That's true.
Yeah. Another question. So since you observe, please mute yourself. My voice is echoing my side. I don't know why. Maybe it's my network. So since you observe exponential multiplying, first find the Laplace of what is multiplying 4t. And this is what? Remember, shine a over s squared minus a squared. So a over s squared minus a squared. Then, how do we now find the Laplace of exponential minus t, shine of 4t? Since exponential multiplying first shifting theorem, this minus 1, come and subtract it here, plus 1 square minus 16. That's it. So when it was 2, we come and subtract it. So when it was minus 1, you come and subtract the minus 1, and that'll give you plus 1.
Can you hear me, sir?
I can. What are you saying? I can hear you now. I can hear you now.
I was not saying anything.
Next. Laplace of exponential minus 2. Okay, so what do we do? Firstly, since exponential, go and find this one. 2 factorial. Then phase shifting property. Now tell me what I'm saying.
S plus 3.
No.
Like 2 over S plus 3. Yes, all raised to power 3.
Exactly. So let me give you your own exponent. Because mute yourself. So since we've learned how to evaluate the Laplace transform, you have observed the property and so on like that. So before we can solve differential equation with Laplace transform, you must learn how to find inverse Laplace transform. It means that probably our next class will be starting with inverse Laplace transform. Yeah, inverse Laplace transform. So whenever we learn inverse Laplace transform, we will now learn how to evaluate differential equation and try to also to learn inverse Laplace transform, try to revise your partial fraction. Very important. Like very, very important. Your own assignment, your own soft assignment is this. Now, so find the Laplace transform of k exponential minus 8t cos omega t. Number 2, find the Laplace transform of sin t cos t. And then find the Laplace transform of 0.5 exponential minus 4.5t sin 2 pi t. I think this thing is okay. Okay, this assignment is okay. Do you have any question?
No, sir.
Yeah. So let me stop the recording. So this is where